pleasure to introduce Pushmeet Kohli from DeepMind. Pushmeet is a true polymath. He started out in verification, and then he moved to optimization, and then to vision, and then to probabilistic programming, and then to program synthesis, and now he's doing verification and security again. So he's sort of like this recurrent neural network that's been running around on a circle. But the amazing thing is that at each point of this walk, he brings in all the knowledge accumulated from previous steps. And so the result is something extremely interesting. So I think Pushmeet is a true leader in this space, and I'm absolutely delighted to introduce him.
Thanks, Varas, for the embarrassing introduction. So the point is that I started off in formal methods, working with Yuri Gurevich, Wolfram Schulte, and in fact, Mayur Nayak and I were interns at MSR. If he, like Mayur, might be hiding somewhere. But we were in that sort of community, and then I, over the last sort of 14, 15 years, moved around in computer vision and machine learning, and then now, I don't think I'm coming back to this field because I think fundamentally machine learning and the whole area of artificial intelligence is deeply sort of related to what we were studying in formal methods and informal verification and program synthesis. So essentially, that's what I will try to sort of try to convince you that this is, we shouldn't be thinking about these problems in two different sort of setups. It's essentially one sort of problem. So I sort of see program synthesis and machine learning and AI as the same sort of problem. So that's what the topic of my talk will be all about. It will be on program synthesis and AGI. So why AGI? Now, DeepMind, the company that I work for, its mission is achieving artificial general intelligence. So what at a very high level is the definition? It's essentially, if you are given a task description, to be able to sort of translate it into an implementation. Now, how this manifests itself in what you might have heard DeepMind doing is if you take an agent and put it in any environment, you should be able to sort of have a policy that that agent sort of executes that does well in that environment. Right? So as a working definition, you can sort of think of that as taking some task description and converting it into an implementation. Now, all of you would sort of recognize that this is what we do in programming, right? We take a task description, and the task description, as many sort of talks have sort of pointed out, can be in various different forms. So the specification can be expressed in various different forms, but essentially the whole idea is to translate it into an implementation which works and solves the problem. So there are two sort of key aspects of the AGI problem, or this solving a general sort of task problem. One is to sort of infer what is the specification that we are interested in, right? So what does the user have in mind, or what is the problem that we are trying to solve? And the second problem is, once we have an understanding of what the problem is, how do you solve it, right? How do you translate the spec into an implementation? So in the AI community, we sort of look at it as inferring the user specifications, and the second is basically how do you make sure that your model or your agent is consistent with the specification. There are a lot of implications into topics like value alignment, that future sort of AI systems should align with the values of the human race, or the user, or the people who developed it, or like the users who are going to use it. So let's talk about the specifying task bit. Now, there are various sort of forms where, if we bring back this discussion into program synthesis, that you can express sort of tasks. So you can express tasks using a complete formal specification. An example of a sort of problem setting is code super optimization. Here you are given a program that actually works. You have a very sort of well thought out formal specification of what the program is supposed to do. You are just supposed to now optimize it, right? Build a better version of that. So it's purely a sort of an implementation problem. You can have partial formal sort of specification where you are given some input-output examples, but those do not cover the whole domain, right? That will be sort of a very difficult thing to do. So you're given some samples in the domain, and you are expected to somehow learn the full mapping. And then the type of specification that we are sort of interested in, we sort of see in coding competitions and what generally programmers in companies are supposed to do, where somebody sort of comes in and says, this is roughly the thing that I want you to sort of develop, and then there's an interactive sort of discussion, mostly sort of sometimes expressed in natural language, and then the programmer is supposed to first figure out what the manager or what the project lead is supposed to be saying, and then secondly translate that specification into an implementation. Now the first problem is essentially a translation problem. It's a pure translation problem, and it's also challenging because it's a very hard search problem, right? But the semantics, you are trying to preserve semantics, and you are trying to sort of translate your specification into an implementation space, and the search space is quite large. So it's a very hard translation and search problem. The second type of problem is a spec inference plus translation problem, where you're trying to sort of, you are given this sort of partial spec, right? You're given some input of examples, but they do not constrain exactly what you want to do. They roughly give you a guide as to what the user might be interested in. And so you're trying to infer the true sort of latent spec that the user might have in mind. And you're supposed to translate that spec into an implementation or into a program. So I would say that's spec inference. But then, even within spec inference, there are two notions. There is a notion of sort of you're trying to generalize. You're trying to sort of find out what the user had in mind through this partial sort of spec that you were given. And then the third sort of thing is spec inference, where you have to assume that you know some knowledge of the world, right? Some common sense reasoning, right? And that's what you sort of see when you are trying to think about programs where you are given very informal specifications in coding competitions and so on, where the user is sort of expecting you to have some sort of notion of the common sense of the universe, right? In order for you to even infer what the user might have in mind. So I'll give you examples of some of the work that we have done in this area, but like it's just snapshots and small sort of directions that we have tried to explore, but there is a lot of work that needs to be done. So how do you specify tasks? I will sort of give examples of using other programs, using examples, using input-output examples, and using language. And I'll talk a bit about this, a little bit more about this, and a lot more about this, right? Because like people in previous sort of speakers have already sort of discussed a lot about examples in other programs, so I'll be more focusing on language. So let's start with using other programs. So a very sort of simple sort of application that I already sort of mentioned in the introduction is code super optimization. So here you are given a program, and you are told, can you find me a more efficient version of this program? Right? And there are systems from the programming languages community which have sort of tried to do this very well. So there's the Stoke sort of a system that came out of Stanford, and there have been a lot of papers in the programming languages community on trying to sort of search effectively in the space of programs to do super optimization. And if you look at it, most of these sort of methods are trying to do some kind of search. And here machine learning can really help, because you can look at the patterns in the program and see whether there are systematic ways in which you can achieve more efficiency. So in this work, which appeared in sort of ICLR 2017, we showed that if you use the normal sort of uniform sampling sort of based rewrite rules that you execute on programs, you get to the optimal at some point of time, or you basically get to some sort of point which you are then evaluating using unit tests or using sort of static verification, static analysis or verification. But if you use an RL model, if you use a learned policy, which is using learned distribution to do rewrite rules, then you do this much more effectively. And so before training, so these lines in this curve show different programs, and how the score or how the time sort of taken by the program sort of changes as you do optimization. So if you start with a uniform sort of policy for applying rewrite rules to the code, you get this sort of curve, and you are seeing that you are making progress but slowly. And this is what our proposal distribution is able to do. So after training on a large bunch of programs, it's able to much more effectively perform these rewrites. But if you think about it, that was just one application. But the whole sort of domain in which RL seems to be applied today, reinforcement learning seems to be applied today, can be broadly sort of considered as learning from complete specifications, because this is what reinforcement learning is all about. You have an agent, and it's interacting with a simulated environment, or like it's not it's in the general sort of case, it's not a simulated environment. It's a general sort of the world or a general environment. It's taking some actions and observing what happens in the environment and observes the reward. A lot of the work that happens in reinforcement learning today is on simulated environments. So if you have simulated environments, you have a full formal characterization of what is happening in the world, right? So think about an Atari game. You have a program that actually sort of captures what's going to happen in an Atari game. So if you're trying to if you're trying to develop an agent which can work well in that simulated environment, you can think of it as an example where you are doing translation. But here you have the full formal specification of what it means to play well, but how do you play well? You're essentially doing a translation problem in some sense. Right? Like it's very hard to, like, nobody sort of thinks it that way, but it's essentially a translation problem that's happening while people are sort of doing reinforcement learning on simulated environments. Right?
Translation from what?
Translation from the reward function and the program, the environmental program, right? The simulator that's running, say, the Atari simulator. So there is code that basically runs Atari, the Atari environment, right? And produces rewards and produces observations. And there's another program which is supposed to interact with this environment and produce the best reward, right? So in some sense, the characterization of the problem is fully specified by the program of the simulator. There was no generalization that needed to be done. It's a pure search problem in some sense.
The spec of the simulated environment describes how the agent should behave.
Exactly.
Although, I mean, in this setting, the simulator is really oracle. It's like the specification is, maybe you have a complete specification, but it's hiding behind this oracle that you only have limited querying access to.
That is true. That is true.
So in a lot of the traditional formal specification synthesis from complete specifications or like code optimization, it's white box.
True. Yeah, so there are different gradations of the problem, right? Where you sort of see it as an oracle, or you can see the whole sort of code base, right? But if you should think of it as a translation problem. One way of thinking about it is a translation problem, but it's different. You are right. In many cases, it's the underlying sort of code for the simulation engine is hiding behind this interface, and you can only query that interface, right? Now, this is work that we did with Swarath. This is another example of the translation problem, but now sort of having an application for machine learning specifically, where you learn a program that mimics a neural policy. So once sort of a neural network has implemented a policy for behaving well in an environment, and you can then sort of translate it into a symbolic sort of form into a program. And Swarath didn't get a chance to sort of talk about this in his talk, so I'll just give sort of a 1 minute sort of summary. Here you are applying reinforcement learning in this environment called Torx, which is sort of a simulator. You look at this car, and the policy sort of drives this car. And what we showed, let me just stop for a moment. So we first sort of train the policy using vanilla reinforcement learning, and not from pixels, right? We can do it from pixels, but here we just do it from the symbolic state, because that was not the point of this sort of investigation. So you train a neural network policy, it drives reasonably well, as you saw. And now what we'll do is basically we'll somehow distill that policy, this very complicated sort of neural network, into a program. So now all the sort of controls or the actions that the agent is taking will be taken by a program, a simple sort of program. And this is how the policy sort of works when sort of written by this program. So you can see that it's much more smooth in how it interacts with the environment. So let me repeat. So the actions here are taken by the neural network, and you can see how jittery they are. And when you sort of translate it into a program, the inductive bias of the program, the regularization that enforces, forces the controller to be much more smooth. Right? So there is some added regularization that happens because of this. Now, another way to demonstrate the effect of this regularization is if you now test both policies, the neural policy and the programmatic policy, on a new track. So if you apply it on a new track, so this is a new track, and so here's the neural network policy, and it will work well for a while, and then it sort of crashes. And this is the programmatic policy that was distilled from the other policy, but then sort of refined. And you can see that it has no problems. So there is sort of this issue of the inductive bias that the programming language sort of accords that makes the policy much more stable. Okay, so that was just about sort of learning from complete sort of specifications. Martin, you had a?
Yeah, just like a quick question on the policy. I was curious, like, does the policy learn to like follow the middle line, or it's more like learning the edges to learn?
No, it's the policy, the neural policy. Its task is to solve the track, right? To basically complete the track in the fastest amount of time without basically crashing. The programmatic policy, how it sort of works, its job is also to solve that particular task, to complete the track, but we guide it through the actions of the neural policy. So you can think of it as imitation learning. So first, the neural policy tries to solve the task, and then the programmatic policy tries to imitate the neural policy. It does sort of, it cannot do a complete job of imitation because it's not expressive enough. So it does some job, and then you sort of and then you start from that procedure to sort of still minimize the reward function. So it's not trying to get to the middle of the track. Its main objective is to sort of solve the track. Swarath, if you want to add.
Yeah. So post fact, if you look at the policies, you can actually interpret them as trying to, you will see that that policy that Pushmeet showed, there are these two branches, and you can interpret these two branches as being close to the middle of the track and being far away from the track, and then under these two circumstances, you do two different things. But there is this restriction built in that there is a sketch that follows kind of sort of the structure of a PID controller.
Yes, I don't know if this question makes sense, but do you end up with a policy that's much more brittle as well? Because you've kind of lost that sort of neural kind of granularity, as it were.
So the neural network is basically much more expressive, right? So it has room to overfit, right? The programmatic sort of policy has limited expressivity. So it might be the case that just because of its limited, so the limited capacity gives it a good inductive bias, so it's able to sort of do well. But there might be, for example, cases that it has never seen, or it has no sort of way of representing. Right? There might be, the environment might be very, very complex, and there is no way to for a programmatic sort of controller to actually express that amount of that sort of richness in the environment, which maybe the neural network policy can do. But in this case, it's sort of a simple environment, so that didn't sort of come out.
I'm confused. So it sounds like the inductive bias in the programmatic learner is small enough that you can search it tractably and find an optimal solution. Why not just learn that directly?
No, so the search space is small, but it's not that small. So that is the baseline, right? So it's a very large sort of search space still, right? And in fact, like as far as we can tell you, right, we did sort of do search directly. Yeah, where you directly sort of say, try to find a programmatic policy which achieves high reward. And without that imitation, without the constraints that, without this guidance of trying to imitate the neural network policy, it does not get off the ground much, right? So the imitation is basically helping narrow the search, right? So that it basically looks at the right sort of areas and then does fine tuning. If you just say, okay, learn me a PID controller, learn me a program directly which minimizes this reward, it just fails.
Okay, so using the gradient descent first as a way to constrain this.
Exactly.
Does all the regularization come from the expressivity of the language, or do you have an additional bias or like short program?
So I think the DSL was expressed in sort of, there was a DSL, and that sort of says that this is the structure of the program, and that's what the program is searching over. Right, that's what the sort of the distillation process is searching over. So in fact, you can have larger programs, but like here we were sort of limiting the program sort of size to some sort of value.
But we did prefer the smaller programs.
Yeah.
So there is a sampling process when you are generating the programs, right, which prefers the smaller ones.
Okay. So now I'll sort of talk about basically specifying tasks using examples, and this might have already been sort of explained by Rishabh. But I'll give you some sort of highlights of what are some important things while you are dealing with tasks where you are dealing with input-output examples. Now, this is where the analogy between program synthesis and machine learning really sort of comes together, right? So this is an example of what we sort of see as a machine learning problem. You are given some images, and you are given some corresponding labels, and you are told build me an image classifier, right? That's what computer vision people, what machine learning people, what deep learning people would actually try to solve, right? And the programming language they use is differentiable, so you can do sort of gradient updates to learn the program and therefore learn neural networks and so on. But at a fundamental level, there is no sort of difference between the program synthesis problem, from example, and deep learning using examples. So in neural program sort of synthesis, we said, okay, let's try to solve a task like this, where you are the conventional sort of tasks for program synthesis, which is the string inference tasks in flash fill, which has been sort of used a lot in the programming languages communities. Just to recap, you are given some inputs, and you are given very limited number of outputs, maybe even one, and a DSL. You are supposed to generate the program, right? So there are two challenges in neural program synthesis, right? One challenge is to make sure that the programs are syntactically correct, and the other is that they are semantically correct. Now, if you think about the program synthesis methods, they almost sort of ensure that you are syntactically correct. But in machine learning, if you generally sort of give it to a neural network and say, here is some spec and produce me a program, and you could use a sequence-to-sequence model, and it could produce gibberish, right? It is not guaranteed to produce programs that are even syntactically correct. So there are two sort of ways that we can reach this. One is syntax consistency through grammar expansion, which is sort of more akin to the types of things that we would do in the PL community. And the other is basically syntax consistency through learning, right? Where you're trying to basically learn what is correct semantics. And this is sort of related to some of the stuff that Iran was talking about in the morning session, right? How can you learn a grammar with just examples? So for working on this, we developed this new type of neural network which can ingest a variable cardinality set of input-output tuples, and that sort of first neural network takes this set of variable cardinality, variable sort of length tuples, and transforms it into a vector. So now you have a vector which actually sort of captures the whole semantics of the partial specification that you had provided. And then there is this recursive reverse recursive network, which essentially generates an AST from that vector representation. So conditioned on that vector representation, you sort of produce a program. And when you look at the numbers, the numbers look good on synthetic data, and it's able to sort of do very well, right? But on synthetic data, on data where we sort of generated the samples from a DSL using some sort of distribution, sampling distribution. When you test this on, and you can get sort of reasonable results, you can see that the AST sort of is constructed in sort of a reasonable sort of way. But when you test this on real world benchmarks, you see that it sort of fails quite miserably on larger programs. And it's not able to sort of do very well, go beyond like the 38% limit because it's just not able to solve any of the lens 15, lens 17, and onward sort of programs. And so there are two sort of steps we took to resolve this sort of problem, and which I can explain using this example. So when a programmer, as a programmer, try to solve this problem, right? So when you're thinking of writing a program for this transformation, you would say, well, first I need to get D. So you basically are focusing your attention. So when you're writing the program, you're focusing your attention on what is the first thing that you need to output. Right? So there is this notion of attention, that you are sort of attending to the right parts of the input, right? And then you say, well, DO, WA, FO, like I can do DO, WA, FO, but then you see LN and you like, okay, this program is inconsistent. So I need to sort of think more broadly, and then you are focusing your attentions on specific sort of rows in the data set, right? And then you figure out, well, that in this sort of carefully chosen sort of program, you wanted the first character to be the initial of the last name, but the second character comes from the second character in the first name, right? But you needed this notion of attention over, you carefully sort of driven notion in order to sort of write that program. And that's what, if you give that sort of capability to a neural network, then it's able to sort of do very well. And in fact, it's not able to not only perform very well on these larger sort of programs, but it's also able to deal with noisy sort of data. And this is again sort of what was shown in Iran's talk as well, that you are able to deal very well with on noisy stuff compared to a pure symbolic approach, because it will fail on like exact match, right? Whenever it does not get the exact match. So you get these sort of good results where as you increase the amount of noisy characters in your inputs and outputs, this model that we have it does not sort of go, it degrades sort of gradually, while a pure symbolic approach would degrade quite badly.
On which axis is the number of examples?
So the number of examples is fixed.
What is it?
It was, I think, 5 or something, 5 or 4.
It's not 500.
Yeah, it's 5 or 4, and then you basically add noise. Okay, so there are some sort of handicaps that this sort of neural agent. So if you call this a neural agent, it's, if you compare it to a human programmer, it has it's using certain advantages. First, it's working on a very simple DSL. It's not working on like C++ or Python and so on. It's working with a simple DSL. It needs the grammar, right? It's basically utilizing the programming language, a full sort of construction of the programming language, and you are giving it sort of programs. You are giving it improper examples and also programs. Now think about a student learning how to program. Now I know a lot of you would are very good at programming in C++ or in some sort of language, I don't know, Haskell and so on, but there are very few of you who could actually write down the full sort of grammar description of the language, right? In fact, I would be surprised if any of you could write the grammar description of the language, right? People, as humans, we don't sort of work with that sort of full grammar. We can infer it. Without knowing it, we can sort of roughly sort of learn to program. And so can these sort of agents do that? That's sort of a question. So to understand these sort of questions, we looked at another sort of environment, and now we are going to use reinforcement learning rather than supervised learning In the previous sort of work, we were just looking at input-output examples, giving the agent supervisory targets of programs and seeing whether it can sort of find out those programs. Now we'll sort of go to reinforcement learning and see whether it can learn to solve these sort of tasks. So for this, we use the Carroll DSL, and now this is slightly more expressive. It has control flow and so on. And it's a sort of language that Rishabh has already sort of spoken about. It's sort of used for teaching the undergraduate course in Stanford. And there are sort of two things that I want to sort of say here. So now you can sort of formulate the program prediction sort of problem. So what is the program that you're going to predict conditioned on the input-output examples? First, you factorize it as into a product of conditional sort of likelihoods of the next symbol given the program you have so far and the input-output examples. And then there are two sort of things. The maximum likelihood sort of model, where you're just sort of finding out, you're trying to maximize the likelihood of the true sort of program token. And the other sort of thing where you are introducing this notion of a reward. And this reward can come from any sort of place. It could be consistency of the produced of the program that you produced and the outputs it's producing and how similar they are to the outputs that we expected and so on. And then you can also incorporate some sort of grammar model in this. And this grammar model can either be very strict. It can say, try to sort of emit symbols which are only consistent with the grammar, with a hand-defined grammar, or try to emit symbols which are consistent with a learned grammar. And there are only sort of two high-level sort of things that I would like to say. One is that learning of this grammar actually works. You can produce reasonably good results without sort of giving an explicit sort of grammar to the model. And in some cases, it actually outperforms. And now this is very counterintuitive. A programmer who is given the option of basically saying, here is the grammar, and told, okay, there is no grammar, but you should try to think about learning a grammar, is able to somehow outperform a person or agent which has access to the full grammar. So what's happening here? So it might be that it's learning sort of a grammar which is not fully complete, but it's somehow aiding its search for a better program. And this is something that we will sort of see in a later slide as well. But this is a very interesting sort of point, that you could sort of restrict your grammar and somehow still sort of reach good performance. And then the other sort of bit is about if you use now this RL-based objective where you're trying to match the outputs that you expect rather than just exact match of the program that was in your training set, then you can do much better, especially for generalization rather than just exact match, right? So there are two sort of tasks. One is, given the input-output examples, produce the exact same program that I expected in the training set, and the other is basically produce the program which is semantically correct and produces roughly the same outputs given the inputs, and this sort of RL objective is able to perform much better for that test. Okay, and so this is, and then we finally come to the point which is like more sort of AI centric, which is specifying tasks using natural language. So here I'm going to sort of talk about two projects. One is a project where now the agent's sort of task is described by a sequence of instructions. So the agent is put in a world, in an environment, and it sees some observation, and it's given some instruction saying pick up sheep, and it has to take some actions to execute that instruction. So think about a future sort of robot in your sort of house, and you say sort of mow the lawn, or basically get me a cup of coffee, and so on, and that's you're trying to build that sort of agent. So there are two forms of generalization you would expect this agent to have. First, you train it with some instructions. So you train it with some instructions. You say at training time, you ask it to execute these instructions, like visit pig, pick up 3 sheep, transform green bot, pick up horse. And at testing, you are now giving it a different set of instructions. So there are two forms of generalization. One is you start with a small set of programs, only like with 4 instructions, and you at test time you can have much larger set of instructions. But there are also instructions it has not seen. So it has probably seen it has seen sort of visit pig and sort of transform cat or like transform sort of pig and visit horse, but it has never seen transform cat. So it has seen all the verbs and it has seen all the nouns in some context, but it has not seen all combinations. And you would expect it to sort of generalize to unseen combinations. So that's the other sort of form of generalization. So how this sort of agent sort of works, it has this sort of meta controller which gets the instruction, and then it sort of interacts with this parameterized skill which somehow allows it to do the stuff and act in the environment. So this is like think of a brain and sort of muscle memory. So the brain is sort of saying now put your leg move here and sort of hand move there and so on, and it's sort of taking care of all the coordination that needs to happen at the reasoning level. So this is how this sort of agent sort of plays. So let me just pause this and sort of explain the task to you first. So this thing here is the agent's view, what the agent actually sees in the environment. So it's a Minecraft universe. It's like a 3D world. And this is the task it's supposed to perform, right? Pick up 2 pigs, transform 3 cats. And this view is only for us, just to see what the agent is doing from the top, right? To see whether it's performing the task well and so on. So the agent basically gets this observation and basically this instruction. And if it follows this stuff during training time, it will get a reward. Only if it does everything correctly will it get a reward, right? But there is a reward function definition, right? This is only a simulation. You cannot do it in the real world because the agent can take millions of trials to actually learn to do this sort of stuff. So let me just play this. So this is how after training it plays. So you can see it's moving about. It's sort of trying to find the pig. It's found one pig, and now it has to transform 3 cats. So it remembers that okay, it has transformed 1 cat, so it shouldn't move the instruction pointer. And then it goes and transforms. Okay, it has to pick the treasure chest as well. So there is a treasure chest, like there are non-deterministic things that treasure chests appear and so on, and it has to sort of get those out of turn. So finally, it sort of now it goes to the sheep, and now this is the generalization to longer instructions. So once it's trained, then sort of now you can see it can generalize to much larger sort of sequences of instructions. And of course, the maps are continuously changing, right? So you train in one sort of environment, and then you test on some other environment. And here it's sort of you are seeing a sort of generalization to instructions that it has never seen. So it has seen all the verbs and on all the nouns, but these combinations it had never seen.
So I'm having trouble understanding why is it relevant that there are sequences of instructions, because they seem to be rather independent. But maybe I don't understand the game.
So the sequences are important because it has to do them in exactly the task is you have to do this task in exactly the same sequence, right? And it has to learn that semantics.
Oh, I see.
Right? It has to learn that basically exactly it is not built in, and it has to learn that it has to count, and only then it should move ahead. And then there are non-deterministic events as well, that there are sometimes treasure boxes appearing, and then it can sort of interrupt its normal line of thinking to deal with these non-deterministic things and so on. So we were testing the agent's ability to infer all these sort of issues. But you cannot implement that in practice because you will need to define a reward function, and you cannot basically build a simulator of your house and where the agent is allowed to interact millions of times and be given rewards for the 10 times it sort of succeeds out of the 10 million trials that it has, while breaking all your furniture in the living room and so on, right? So that doesn't work in the real world. So how can we make sure that we can do training where you don't even have a reward you cannot even specify a reward function? So this is an example where you might say to the robot, fold me a towel in a fancy way, right? And you don't even know how to define fancy way. And you might not even know how to define, how to actually fold your own towel in a fancy way. So you can't even do imitation learning. So you can't sort of even show it sort of samples of how to do that, perform that behavior. So as any sort of respectable robot would do, when faced with this instruction, it will do sort of a Google search and say, okay, let me sort of find out what fancy sort of towels look like. And so these are sort of then examples of some sort of goal states. So it now knows I need to reach this particular point. So starting from any sort of point, I need to reach this sort of point. So I will not, I'm not given any reward functions. I'm just given these sort of examples of goal states, and I have to sort of recover some abstract notions of what it means to succeed at the task, and then try to replicate those sort of abstractions in the new domain that I'm sort of given. So to test this type of generalization, we gave this sort of agent, we showed it certain sort of images. We showed it what it looks like to be an eel or a diagonal line or a diagonal connect or a snake shape or a line shape or a triangle shape and so on. So we just gave it these notions of this is what a triangle looks like made of blocks, this is what a circle looks like, and so on. And then its job is, given sort of some environment like this, where the blocks are sort of scattered, and there might even be sort of other distracting objects in the environment, it has to somehow act in the world, sort of pick up the boxes, put them into the right place, and construct the task that it was given, right? So in this case, it was told build a triangle, so it has to sort of go in, pick up the blocks and put them into a triangle sort of shape. And here it's suppose diagonal line, so it has to know that basically there needs to be a line, that the line should be connected. If it is a diagonal line without connected, then it will get no reward, and so on. So it has to learn all these sort of things. And so again, this notion of now if you don't have a reward, how do you sort of learn without a reward? And so the agent sort of in this case sort of works according to this, right? So it has a policy, and it's again sort of interacting with this environment, right? But this environment does not give rewards, so it has to learn its own reward function. So simultaneously, sort of in this case, the environment only gives an observation. So it has to learn its own reward model, which compares, whose job is to take the instruction and state, and figure out whether the current state of the environment is consistent with the instruction that I've been given, right? So it has to learn this sort of reward model. So now can we do policy learning with this sort of hybrid setup, where you're only getting, the environment is only giving you observations but not giving you the reward function, and you are trying to learn the reward function. So this is how it sort of looks like. So here you say make a diagonal line, and it's making here a green snake. Here it says connect the green blocks, so it has to know this the topology of like what does it mean to be connect. So blue triangle. Connect the red blocks, so it has to now connect the red blocks, and so on. So what are the challenges, right? So we have talked about like how program synthesis and sort of machine learning are sort of coming together, right? And there are a lot of sort of complicated tasks that we can now solve, which earlier either machine learning nor sort of program synthesis could solve. But now coming together, they can solve a lot more sort of tasks. So what are the challenges? The challenges are that as these systems become more sophisticated and they start getting deployed, you see all types of issues that emerging, right? So and these sort of issues sort of emerged when we did when we first deployed software in the real world. We saw there are a lot of types of bugs and so on. But at that point of time, programs were only being deployed by a few sort of people in a few sort of they were like I don't know like 50 computers and so on. And now there are sort of 50 billion computers in the world, or even more than that. So it's very difficult to sort of understand what are the implications. And all the sort of questions of software reliability and verification become really, really important. So we need to sort of make sure that our AI systems are robust to adversaries, generalize well to to variation present in the real world, are not fair, are not unfair, are compliant with regulations. And so there are these notions of, first, how do you formalize these specifications? And then the second is, how do you do this program synthesis or AI synthesis which is consistent with these specifications? So I know like Sanjit has done a lot of work in this space, and sort of Martin is doing a lot of work in this space on sort of developing more rigorous evaluation methods, developing robust AIs and verification AIs. These are sort of topics we are interested in as well at DeepMind. So finally, to sort of conclude, I think program synthesis is a very rich problem, and there are notions. It's not just a search problem, but it requires sort of learning abstractions for planning and reasoning. It requires sort of language understanding, specification learning, and so on. So there are different sort of challenges. And the key question is, as we sort of democratize programming, right, by sort of expanding the universe of specifications, where we include natural language, we include examples. How do we make sure that users, like, I mean, I'm not using the word programmers, because users, in the end, basically now users will become the end programmers, and how do they test or debug their models and verify that the behavior is consistent with what they had in mind? So yeah, with that, that's it. So I think, yeah. So I think, like anything, when people sort of specify a big umbrella sort of term to describe a complicated sort of process, then it's it's hard to sort of make general claims, right? So reinforcement learning is sort of a paradigm in some sense, right? There are so many sort of methods that go into it. So there are a lot of challenges in terms of the domain, right? There is, in reinforcement learning, there are so many challenges in terms of the exploration problem, right? The planning problem, and then sort of the generalization problem, right? So my experience is that if you understand the individual sort of challenges associated with the domain very well, and if you have put in the right inductive biases, and so that you have a reasonable chance of succeeding at the planning problem, succeeding at the exploration problem, succeeding at the generalization problem, then it will work. But if you basically come in and say, okay, here's reinforcement learning, here's SARSA, like I have some functional approximator, throw it on my domain, and it should work, it will not work. It should not work, in fact, right? Because it does not have the right inductive bias and so on, right? Why should a convolutional network with some sort of exploration strategy sort of work on anything in the universe? No, it should not, right? So that's what my take is, that when you think about it sort of deeply and sort of look at the specific problem and say, what is the right regularization, right? People use convolutional networks for sort of things which are translation invariants. Yeah, very good. But if you are working with graphical structures like program and source code, right, then you need other types of inductive biases, like you need graph networks, right, and so on. So if you understand those sort of issues, and you understand the underlying difficulty of the problem, and then you have ways of tackling that difficulty in the inductive biases, in the planning sort of algorithms that you use, in the abstractions that you try to sort of learn or build in, then I think it works.
So then in your latest paper, you have shown that you have used policy gradient with discriminator structure.
Mm-hmm.
So discriminator is basically giving you what you have to do, and then policy gradient is guiding that what you should do next.
Yeah.
But I'm not sure how you avoid that when you have false negative or false positive examples, because that might screw the discriminator, and the policy gradient will go towards negative.
Yeah. So like the question is on this specific sort of path. So you have this policy, right? This agent which was trying to achieve something, right? And it needed to have a good notion of what it was trying to achieve. which was coming from the reward function. And when the process sort of starts, the reward function is sort of correct, right? It's not correct in the sense, but the reward function is partially specified, but what it is partially specified is correct. It was given correct examples of what it meant to be a proper goal state, right? Now, in the process of the sort of learning, new sort of states are being added to train the discriminator or the reward function. And it might be misguided. So think about humans, right? So somebody sort of tells you, in order to sort of achieve success, like this is one sort of ideal of success, right? And so over time, you might say, oh, this is where I have to reach. But over time, basically, you might get to states which you had no notion about, right? Which are actually very bad states, right? You might sort of you might work too hard and your health might suffer, and that was not included in the training data, right? That you could sort of have that sort of issue here as well, but you can avoid it by having the right inductive bias, or having sort of a larger sort of proportion of examples to guide your reward function in the first place.
Unfortunately, we are over time, so we can take maybe one quick question.
So in AlphaGo, AlphaZero, this reward was given specifically for the states, right? So if you were to apply something like that, then you could potentially avoid that step and just give some information about the very end positions, or?
Yeah. So see, the point is, wherever a reward function is given to you, just use it. Right? In AlphaGo, it's a simulator, right? So you have a simulation environment, and you are doing self-play, right? So you are trying to beat sort of, in some sense, you know the whole characterization of who you are trying to beat.
I guess I'm just not understanding entirely why the data set of instruction and goal state is so much easier to come by than the actual.
So exactly in this case, right? So for example, the fancy towel stuff.
Okay,
right, so I cannot sort of give trajectories because I don't know how to do it. I can give you examples of goal states, and I can basically give corresponding instructions, right?
Okay, let's thank Pushmeet.